So, welcome back. In this lecture, I am going to spend time to illustrate the use of traditional approach for calculating phase equilibria method, that is phi gamma approach. Okay. So, let us start again by looking at the definition or the expression for fugacity. Okay. So, so let me first write down the fugacity expression for Weber phase. So, yi multiplied by p would be a simple Lewis fugacity rule, but then we multiply phi I also, which is a correction to this, okay, which is nothing but fugacity coefficient. Now, this fugacity coefficient also depends on temperature, pressure and composition. So, I am going to write that. Okay. Now, this traditional approach, phi gamma approach, which we say make use of different models or for liquid and for vapor. Okay. So, we will try to make use of this, but let me just first build the base for that. For liquid, we know that FL pure I temperature pressure is Pi sat T phi I sat, okay, again a T, and then you have this Poynting correction exponential from Pi sat to P VIL, that is molar volume liquid, RT dP. Okay. If so, what we are going to do is a bit deviate from this and ask this question: if Lewis fugacity rule were applicable, then we would have FIL TPX as Xi times fugacity of liquid pure I Tp, right. That is what the fugacity, Lewis fugacity rule says. And this we have defined earlier also, and then I am going to define it again, that in general we defined activity coefficient, which basically nothing but illustrate the deviation from this Lewis fugacity rule. Okay. This is basically the ideal liquid will behave like Lewis fugacity expressions. Okay. So, this we defined activity coefficient gamma I is equal to gamma I Tp x, which is nothing but FIL Tpx divided by FIL pure I Tp and as well as Xi. This is 6, 7 and 8, and this is basically 9. Yes, Lewis fugacity rule becomes the basis for getting the Raoult's law. So, Lewis fugacity is nothing but it tells you the system behaves like ideal system. Okay. So, now given this expression of gamma, you can write down FIL as nothing but Xi gamma I FL pure I at T and P. Since it is pure, that is why there is no composition. Okay. And now I can plug in the expression of FL pure, which is this, okay, at a given temperature, pressure away from the P sat, right. So, now I can plug in and I get an expression which is the following: gamma I. Now, gamma I, since FL is depends on FTPX, gamma I also depends on TPX. So, gamma I, which depends on TPX, when I am writing here x is basically nothing but composition. Okay. Pi sat temperature, phi I sat temperature, and exponential Pi sat P VL by RT and dP. Okay. Now, this is my FL, right, this is my equation 10. Now, given this expression and given the fact that you have written this already for this, which is for vapor, right. Now, for condition of equality, you need fugacity should be same in the vapor and phase. That means you can equate equation 6 and equation 10. So, you get a final expression, hence VLE requires the following condition to be met, okay, which is Yi phi I Tpx y P is gamma I this Tpx Pi sat T phi I sat T and exponential term okay. It's not be clear, but you got the idea. This is nothing but the Poynting correction. So, this is the final expression of this. Okay. From here you can also get the Rawls law, okay, by considering phi I to be 1. Okay. So, if you consider phi I to be 1, which is basically the ideal condition of the vapor, gamma to be 1, again ideal solution, and then you can consider again phi I sat to be 1, assuming the saturated vapor fugacity is 1, which means again is ideal, and then you can consider Poynting correction to be 1. Okay. Yi P is psi, which is nothing but Rawls law. Okay. All right. Now, so let us take this and we can consider a system which are of similar type. Let us say a case of benzene and toluene. Okay. This is a familiar case. Again, we are considering pressures to be small. Okay, this familiar example is the one which we have similar kind of molecules, similar sizes, which in this case let us say is benzene, toluene. Okay. And my question is that can we find out for such a system pressure versus composition plots, okay, for vapor case and for liquid case. So, assuming these pressures are small, okay, if pressures are small and we have already considered pressure is very low, and we know what kind of approximation we can make for low pressures, ideal, okay, gases, ideal vapor phase we can behave like an ideal. So, phi I Tp y for vapor and as well as phi sat T, both we can approximate to be 1. Since it is a low pressure, the exponential Pi sat till P, this is also we can approximate. Now, since benzene and toluene are of similar chemical nature and type and sizes, we can also approximate gamma Tp x. Okay. So, we got this same Rawls expression. Okay. So, these are the basic assumptions which we have made, but it depends on what kind of system we can do. Now, let us try to come up with an expression where we can draw it also. So, what we are interested is basically Px curve and Py curve. This is what we are interested at a given temperature, okay, at a given T. Okay. So, let us consider P. Now, P is nothing but Yi Ip. So, that is Y P plus Y2P, because it is a binary mixture. Okay. So, P is equal to Y1P and Y2P. Temperature is fixed. For a given temperature, we know the P sats are going to be fixed, okay, because this is for the pure system, P1 sat is for the pure system. So, which means basically P1 sat and P2 sat are fixed. Okay. So, now I can write this as x1 P1 sat plus x2 P2 sat. Okay. I can also write as P2 sat plus x1 P1 sat minus P1 P2 sat. Okay, this is your Px curve, okay, which is a linear, clearly, right. Okay, now my interest is Py curve. So, I can write y1 as x1 P1 sat divided by P. I will start with this. Now, this I can write as a P as P2 sat plus x1 P1 sat minus P2 sat, okay, and this is x1 P1 sat. Okay. You rearrange this. If you rearrange this, what you get? P can be shown, we can show this a bit more exercise. P can be shown as P1 sat P2 sat divided by P1 sat y1 P2 sat minus P1 sat. Okay. So, you can actually do little bit of exercise here, because for each of them you can write x1 P1 sat, you can write it as y1 P, right, and x1 P2, x1 can be written as in terms of x2, okay, and you can redo this exercise to get this expression. So, these two expressions which you got, okay, Px and Py, you can plot it, and if you plot, this is how it looks like. Okay, so this is your pressure, this is your x1 or y1 y. Okay, instead of dividing it, I will say x or y, right, and this is how it looks. So, for the case of this system, okay, I get this kind of expression. Okay. So, of course, this linear will be Px and this will be your Py. Okay. So, this is the example based on Raoult's law, but the approximation which we have made, of course, is a spatial approximation. It is not valid for all the systems. So, if you do not, let us assume that if you have equational state available with you, so you can make use of equational state to solve a problem instead of just making such an approximation. Okay. So, let me try also that example. So, here the example is related to so this is example which states that the species 1 and 2, okay, in the gas phase obey the following equation. Okay, where so z is nothing but the compressibility factor, alpha is summation yi yj alpha ij. Since it is a binary mixture, okay, we know this how to sum it up easily, and we need three variables, because if it is a binary mixture we need alpha 1 2, which is minus 150 cubic centimeter per mole, alpha 2 2, which is minus 270 cubic centimeter per mole, alpha 2 1, which is minus 240 cubic centimeter per mole. Okay. So, what is the question? The question is, what is the dew point symmetric? This must have been alpha 11. Okay. Alpha 11 is minus 150 cubic centimeter per mole, alpha 22 is minus 270 cubic centimeter per mole, after 21 is minus 240 cubic centimeter per mole. Okay. And alpha 21 is basically nothing but alpha 12. So, what is the dew point of a 60-40 mixture at pressure is 20 atmosphere? Okay. Now, what we have been given, what we have been asked is basically that you can make use of ideal solution. So, we can assume ideal liquid mixture, which means basically gamma I is basically 0. So, gammas are 0. What are the things which we have been given, what are the things which are given to us is the relation of pressure and temperature for the vapor phase in terms of the following expression, which is what are these expression? It's Anton equation. Okay. All right. So, the question is now well posed. Z is given, alphas are known, 40, 60, gamma and all this information. So, how do we go about it? From where we should start? We must start first from our definition of the equality conditions, right, here, right. So, this is one. What about this? Okay, fugacity, we have to worry about it, but what about this? And of course, we have Poynting correction. Now, what we can do is we can start with certain assumptions. We also have to make certain assumptions. Okay, what we are going to say is the following, that of course, we have been given that gamma I is going to be 1. So, gamma I Tpx is 1. Okay. We assume that phi I sat is 1. Okay. That means ideal saturated pure vapor, because this is for the pure vapor, right, pure vapor at system temperature, and then you have this Poynting correction Pi sat P VIL RT dP. Okay. So, this is for ideal liquid phase, this is for ideal saturated pure vapor at our system temperature. Okay. And this is the low pressure. Okay. So, this is the assumption. If we do that, what we the low pressure, because 20 atmosphere is still reasonably low pressure. Now, we obtain the following expression yi phi I Tpy pressure, and this is equal to xi Pi sat. So, this is our final expression. Okay. Now, from where, what else we can do? What else we can find out? We have to find out, well, the phi I. So, we can avail the expression which we have written for fugacity, which related to the volumetric partial molar volumes. So, we can actually write down the following expression. Now, recall that we have RT Fi or phi, which is nothing but Fi divided by P is 0 to P Vi bar minus, right. So, now because see, the reason why we made use of it is because this is nothing but, what is this? This is phi, right. So, but we have been given this also, right, the compressibility. So, with compressibility we can directly use here, rearranging this term, and we can obtain our values. It is little tricky because it takes time to do that. Now, Vi bar is del V by del N I TP and rest of the Ni Nj not equal to Ni. Okay, so this given this expression of compressibility, you can show that, which is actually multiple step derivation, that this is equal to 2 times summation yi alpha ij, okay, or in this case yj, j is equal to 1 to 2 minus alpha, okay. Alpha is basically the sum of the values, right. So this I'm not deriving it, okay. This you can find it out by doing the exercise. Okay, what is alpha here? Alpha is y1 square 1 1 plus 2 y1 y2 alpha 1 2 plus y2 alpha 2 2. You can plug in these values of y's because and as well as alpha, because you know this, okay. Y's are given to you. This becomes 212.4. Okay, now phi is the expression of phi based on this, when you plug in there, is nothing, it comes out to be exponential p by RT to summation y, let us say k, because this is I, remember this is I. So, with here I am putting y k alpha I k minus alpha, okay. This is the expression which comes out to be after plugging this Vi bar. If you plug in the equation, you get this expression of phi I. Now, with this information, you can write down phi 1 and phi 2. So, phi 1 is going to be exponential 20 is the pressure, okay. So, we are going to put it in the way the units are in atmospheric unit, the R, and 2 times y1 alpha 1 1 plus y2 alpha 1 2 plus 212.4, which is alpha, okay. This comes out to be exponential minus 38.9 by t. Similarly, phi 2 is exponential minus 71.1 by t, okay. So, for the case of species 1, this we can write y1 phi 1, right. So, this is species 1. Now, you can plug in these expressions, right. So, you have 0.6 exponential. So, we are considering species 1 0.6, species 2 0.4, 0.6 exponential minus 38.9 by t multiplied by 20, again in atmospheric term. This is exponential, this is x1. And what about P1 sat? P1 sat is, since from the Antoine expression we have this information, right. So, we can plug in there. Okay. So, this is the value. For species 2, I am going to write directly. Okay, for species 2, 0.4 exponential minus 71.1 by t multiplied by 20. This is x2 exponential 9.1 minus 3500 by t. Now, these two expressions we can rearrange, okay. If you rearrange expression, we get x1 and x2 as a function of expressions, right. So, you can rearrange, right, okay. And then we can make use of the fact that x1 plus x2 is equal to be 1, okay, which in this case is 0.00089 8 exponential this term which is 2961 by t plus 0.000893 exponential 3429 by t is equal to 1. Now, it is very straightforward. This is the expression. You can plug in this in Excel and find out the temperature. Once you find out the temperature, you plug back and get your expression of x and t. So, thus you can use any Excel sheet or write a program and obtain from here temperature. Once you obtain, you get your xis. Okay. So, this is a very simple way of doing this exercise. I hope you really understood the procedure of doing such a problem, but we will be looking at more algorithmic wise in the next lecture for obtaining it more complex conditions where the approximations are not so straightforward using phi gamma approach. So, I will see you in the next lecture.